Hello and welcome back. Today we are going to discuss about memory management in Spark. We are going to see some reasons for out of memory error in Spark. Now, we all know that executors have facility to spill the data in case the memory is not sufficient, but there are still out of memory errors. Today we are going to see some practical examples for that. We are going to understand all of this in theory and in practical. So, I would recommend you to go ahead and watch this video till the end. Before we can begin with this, if you have not seen our previous videos, go ahead and click the I button at the tip. So without any further delay, let's go ahead and break some executors in Spark. Now, before we can start with practicals, it is important that we understand all of this in theory. So we are going to expand each section of the memory until we reach the last. Okay, so we all know that Spark program requires driver and executors. Now, consider a case you have requested two executors, each with 512 MB memory and 4 cores. Now, it is the duty of your resource manager to go ahead and allocate all of this on the worker node. Now, your cluster runs on the worker nodes, right? So consider you have two worker nodes, worker 1 and worker 2. Now, once you request for an executor, a JVM process is created in the worker node. It is with of the same memory that you request for. So, since we are requesting two executors, you can see two JVM process gets created in each of the worker node. Now, the memory would be around 512 MB each. Okay. Now, these are all JVM process. Okay. Now, since this is JVM process, the memory for this would be known as JVM heap. Okay. Now, there are basically two types of JVM heap. One is on-heap and the other one is off-heap. So, if we discuss about on-heap and off-heap, on-heap is the default memory. Okay. And off-heap is something which is managed by OS. And the on-heap is managed by JVM itself. Now, the off-heap is disabled by default. So if you want to use off-heap memory for Spark, you have to first enable it. Okay. Now we are not going to discuss off-heap right now, but we will be discussing more on on-heap. Now, once you request for this 512 MB memory, this is the default on-heap memory that will be generated. Okay. Now, consider a case you requested for 512 MB memory for an executor. So the JVM would not allow you to get 100% 512 MB. Rather, it would only give you 89% of that. Okay. And the rest 11% which is left is used by the JVM in-house process like garbage collection. Okay. So you will have only usable amount of memory which results to 89%. Okay. So let's calculate the 89% of 512 MB, which would be around 455.69 MB. Okay. So this is the usable memory you can go ahead and use further. Okay. So let's visualize this. So I'll just expand this memory now. Consider this was whole 512 MB memory that you requested for an executor. So you will only get 89%. Okay. So this is 89%. And the rest 11% is taken by JVM for its own in-house process. Okay. And this 89% is around 455.69 MB. Okay. So now we understand that this is the usable memory that you can go ahead and use further. Let's expand this now. Now, once you have this 455.69 MB memory, again, you cannot go ahead and use all of this memory for Spark. Spark reserves some of the memory for its internals, which is known as reserve memory, and the size is 300 MB. Okay, so this is set to 300 MB for reserve memory. Now, the use of reserve memory is to store Spark internals. Okay, now the rest amount of memory which is left is 155.69. We can go ahead and use further. Before that, let me tell you one more concept. The minimum amount of memory for an executor that you can request is 1.5 times of the reserve memory. Okay, now we know that the reserve memory is set to 300 MB, so it would be 1.5 into 300 MB, that will result to 450 MB. Okay, it simply means that you cannot create any executor with memory less than 450 MB. That would not work. So the minimum amount of memory that you need to provide for an executor is 450 MB. Okay, this has been set. Now let's go ahead and expand the rest amount of memory that we have, which is 155.69 MB. So let me just go ahead and expand this further. Now this is our total 155.69 MB memory. Okay, again, you cannot go ahead and use all of this. We have a split of 60-40. Okay, 40% is used by user memory. Okay, and the rest 60% is used by unified Spark memory, which is also known as Spark memory. Okay, now before we decide the numbers, let's understand what is the use of user memory and what is the use of Spark memory. Spark memory is something that would be used by Spark, and Spark has 100% control on top of Spark memory. But the user memory is something which Spark does not have control over. Okay, and this is generally used to store user data structures and UDFs. Okay, and Spark does not have control on top of this. It has only control over this unified memory. Now let's understand this 60-40 split. This would be approximately 93.4 MB memory, and it is 62.28 MB. Okay, now how do we decide this is 60-40? There is a configuration which is called as spark dot memory dot fraction. Okay, it is set to 0.6. Okay, it means whatever memory is there, you just multiply it with 0.6. That would be the memory for Spark Unified. Okay, rest would be used by user memory. So our 60% here is used by Spark, and the rest 40% is used by user memory. If you want to change this configuration, you have to go ahead and change this particular Spark configuration. If you change it to 80%, your Spark memory would be 80%. The default value is set to 0.6. Okay, now we have the Spark unified memory. What does this unified means? This simply means this particular memory has two portions. One is known as storage and the other one is execution. Okay, now let's go ahead and split this further. So if I expand this unified memory further, consider this is our whole unified memory. So the size for this complete memory is 93.4 MB. Okay, now both storage and execution uses this memory, and this is very important to understand. Consider the left hand side we talk is the storage memory. Okay, and the right hand side is execution. We can go ahead and put a boundary here. Okay, but this is not a hard boundary. Now this boundary can shift to right or left as per the requirement. In case storage requires more memory, this boundary would shift to right. In case execution requires more memory, this boundary would shift to left. But there are some limitations or some restrictions to it. Okay, and we are going to discuss this further. Before that, let me tell you what this storage memory is used for, what this execution memory is used for. So the storage memory is generally used to cache your data. Okay, so whenever you cache your data, all of those cache data goes into storage memory. The execution memory holds all of the data that is required for execution, like your hash tables, like your aggregation data, like your shuffle data. Okay, so whenever it requires shuffling, it pulls in the shuffle data. All of this data gets stored in execution memory, and this is very important, and it is always given priority. Okay, now we are going to discuss about this, but before that, this is how these memories are getting used. Now as we said, this is whole is a unified memory. What does it exactly means? So consider you go ahead and cache some data. Okay, in that case, whole of your cache partitions will get stored in storage memory. Okay, now consider this does not fit in memory, it requires more memory. So you can go ahead and consume the memory from execution, given this memory on the right hand side is free. So consider the execution is right now using only this much of memory. In that case, this particular split can shift to right here, and storage can go ahead and consume some memory from execution. Okay, so this is where it is unified. It can go ahead and consume some memory from execution. But now consider execution memory grows and it requires more memory. In this case, execution will try to claim back its space, and storage has to evict the memory it has consumed. Okay, so this particular partition will get evicted. okay, based on LRU mechanism. LRU means least recently used. Whatever would be the least recently used, that would be evicted first. Okay, so it has to go ahead and evict and empty the space for execution. Okay, and then this particular split will go ahead and shift to write. So consider both of the splits are evicted from here. Okay, now execution will go ahead and consume all of the memory whatever is left. Now execution can go ahead and consume the memory further on the left hand side. For example, execution try to go ahead and consume more memory on the left hand side, but given it is free. If it is not free, then execution can only go ahead and consume up to 50% of this unified memory. And this is configured by a parameter which is known as spark.memory.storage fraction. Okay, which is 0.5. It means 50% of the memory is immune to eviction. It means the storage memory can consume up to 50%, and if it is full, execution cannot go ahead and evict the data from storage. Now consider a case if the storage is already empty like this. In this case, this particular split can go ahead and shift to left, and execution can go ahead and consume the remaining amount from storage, given this is free. If it is not free, then you can go ahead and consume up to only 50%. Okay, rest 50%, if it is full, is immune to eviction, and this is what this configuration tells you about. Okay, now in any case, execution is always given priority. For example, execution is consuming around 70% of the memory, and only 30% is being right now used by storage. But storage now needs more memory. For example, it needs to store more 20%, but it cannot do it until execution is complete and it frees up the memory. So storage cannot go ahead and evict execution memories. Okay, so storage cannot evict execution. Okay, but execution can evict storage if it is consuming the memory from the execution side. Okay, so this is important to understand. Storage has to wait until execution frees up the memory. Cannot go ahead and evict execution data out of the memory. Okay, so this is how this whole unified memory works. So if I summarize this whole, both storage and execution can expand to left and right as per their requirement, given either one is free. Okay, now if storage requires more memory and execution is free, storage can shift to right as per the requirement. Okay, and once executions requires more memory, it will start evicting the data which is being consumed by the storage. Now, if execution requires more memory, it can shift to left, given the memory is free. And if it has already occupied some of the memory from storage, and storage wants more memory, it has to wait until execution frees up the memory. It cannot go ahead and forcefully evict execution data out of the memory. Okay, so this is important to understand. Now, there are cases when storage will spill data to disk. So let's consider what is that scenario. For example, our split is around 50%. Okay, now this is the 46.7 MB memory, and this is also the 46.7 MB memory. Now again, this is not a hard split. Okay, consider right now execution is only using 46.7 MB memory. Okay, so it has already occupied the space it requires. Now, storage requires more memory than 46.7. For example, it has partitions which has to occupy around 60 MB of data. So it can go ahead and use its own space like this. Okay, now the remaining partitions would not fit in storage memory. In that case, storage will go ahead and spill the data to disk. Okay, and this spillage will only happen if your caching mechanism is defined as memory and disk. Okay, now consider you have defined your caching mechanism as memory only. In that case, you are in trouble. So it will go ahead and recycle the existing space, and if it is not able to do that, it will run into out of memory errors. Okay, so it is very important that whatever caching mechanism you set, if there is a spillage required, you set it to memory and disk. Okay, now this spillage will happen in serialized and deserialized format. So whenever the data gets stored into memory, it is stored in deserialized format. Okay, and the deserialized format is Java objects. Okay, so your data gets stored into native Java objects, but whenever it is spilled to disk, this gets serialized. It means it gets converted into byte streams. Okay, now if you see, there is a conversion happening while writing data to disk, and this is where this deserialization and serialization is a costly operation because it requires resources and it also requires time. So whenever there is a spill happening, Spark has to serialize the data before writing it to disk. Okay, and whenever it needs to read that data back, it again has to deserialize the data in the memory. So this deserialization and serialization operation is costly. Okay, and this is the reason we avoid spills. Now, if you notice, this is the spill on the storage side, right? But we also know that the tasks or the executions also spills data while executing, right? Let's go ahead and understand the scenario where the spill is happening for execution. Now, before we understand the spillage at the execution side, there is one more unified concept that we have to understand. Now, we have this complete execution memory. For example, this is whole our execution memory. Okay, now this execution memory is being used by the cores, right? For example, your machine has 4 cores. Okay, in that case, this whole execution memory will get splitted into equal 4 divisions. Okay, so for example, this is 40 MB. In that case, each of the tasks would around have 10 MB of memory. Okay, so each core can execute its own task with the 10 MB of memory. But what if you have 2 cores? In that case, this whole execution memory will get splitted into half. Each of the task or core will have around 20 MB of memory. Okay, so it is always that the resource or the execution memory is splitted into the number of cores. Now, in case your execution is only running with 1 core, in that case, this whole 40 MB execution memory would be available to that particular core or particular task. Okay, so in this case, if you see, this memory gets divided accordingly as per the number of tasks or the cores requires it. Okay, now let's understand what happens in case of execution spill. So consider this is our execution memory. Okay, now we are completely talking about execution now. So this is whole our execution memory. Okay, now you have 2 tasks running it. For example, you have 2 cores and you are processing 2 partitions of data. Okay, so 2 tasks would be running in parallel. Now consider this whole execution memory is around of 40 MB. Okay, so each task would have around 20 MB of memory here. Okay, so you will have one task running here, the second task running here. Okay, now consider this is the partition for the first task, which is around 25 MB. And again, this is the partition that is being read by the second partition, which is around 5 MB. So they are going to process this partition of data. Now, each partition of data consists of records or rows, right? Now, if you notice something here, we already have skewed data. It means this is 25 MB, this is 5 MB. In this case, this memory size is 20 MB, but it is processing a partition of 25 MB. This particular partition will not fit in the memory itself. So it has to go ahead and spill the data to disk. Okay, again, the spilling has to happen with serialized format. So right now, whatever we are talking about is deserialized format. For example, the memory is total 20 MB and this data is deserialized format 25 MB. Okay, now this data cannot fit into the memory, so it has to get spilled to disk. And while this spillage happens, this will happen in serialized format. Okay, now we already know what is the difference between deserialized and serialized format. In this case, there will be no spillage because 5 MB can very well fit into the 20 MB, right? So there will be no spillage happening for the second task. Now, if you notice, this is a bigger partition, this is a smaller partition, and this is what we call as data skewness. Okay, because of skewed data, the partition is not able to fit into memory and it is getting spilled. Okay, now let's consider one more scenario. Consider the records in each of the partition is such big that it cannot fit in the memory. For example, this particular record itself is 25 MB. Okay, so each of the record in this particular partition is 25 MB. So this partition will now be more than 25 MB. Let's consider an example where you have a partition where you have 3 records in that partition and each record is 25 MB. Okay, now if you try to put this whole record into the memory, it will not fit. Okay, in this case, Spark will run into out of memory error because it cannot split a record. It can spill a partition to disk and read records one by one. Okay, but if the record itself is greater than the size of the memory, it cannot fit in the memory and it would run out of memory errors. Okay, so this is one of the reason when you will see out of memory errors in Spark. Now consider a case where you are doing wide operation. Wide operation means the operation which would require shuffle data. Okay, now in your wide operation you cannot avoid, but you have to bring in all the shuffle data in the memory for the next computation. Okay, and you are generating too much shuffle data which is greater than the size of the memory. In that case as well, you will see out of memory errors. Okay, now consider one more scenario. Consider you are using a broadcast variable. Okay, in that case, particular broadcast variable, if the size is greater than the memory, it would not fit in the memory. Again, this would result in out of memory error. Okay, now let's consider one more scenario where data explosion happens. For example, consider each of your record is around 10 MB. Okay, and now you are doing some cross join or some explode operation which is leading to multiplication of the record. Consider this particular record is getting exploded 20 times. It means this is getting multiplied 20 times because of some explode operation. So in this case, if you see, this would result in around 200 MB of memory. Okay, and it has to fit all of this in the memory in order to work. And in this case as well, you will see out of memory errors. Now, such operations like cross joins and explode needs to be handled properly, because this would lead to explosion of data and this would lead to multiplication as well, and this might lead into out of memory errors if you are not handling those particular operations properly. Now there is one more reason. For example, you have encoded a particular piece of data and zipped in such a format this size is 2 MB for now, but once you bring in this memory and unzip it, it expands to 300 MB. Okay, in those cases as well, you can see out of memory errors. Okay, now very good example for this is you zip Parquet in snappy format. Okay, but you can go ahead and zip this in zip as well. So you have to be very careful about the zipping that you are going to use. If it results in too much expansion of data, it can also result in out of memory errors. Okay, so these are some of the few examples in which you can very well see out of memory errors if the data does not fit in memory. Today we are going to see one of those examples and we are going to understand how you can avoid out of memory errors. It is not always that you have to expand your memory in order to handle out of memory errors. Sometimes a bad code can also result in out of memory errors. And today we are going to handle one such scenario. Now, before we go ahead into this, there is one more thing I need to discuss, which is serialization and deserialization. So, whenever you store your data in memory, that gets stored in Java object format. Okay, but whenever you spill or write the data to disk, that gets converted into byte stream. Okay, so this conversion from memory to disk is known as serialization, and this conversion back from byte stream to memory Java objects is known as deserialization. But you have to note this operation is costly because it requires resources plus time. Okay, every time a data is read from disk to memory, it is always deserialized, and similarly every time a data is being written into disk, it is serialized. Okay, so this is what serialization and deserialization means. Now there is one more concept which is left, is off-heap memory. Let's understand what is off-heap memory. Now off-heap memory is something which is managed by OS and it is by default visible in Spark. In case you want to use off-heap memory, you have to go ahead and set two Spark configurations. The first one is spark.memory.offheap.enabled, and you have to set this to true. Okay, after setting this to true, you have to define the size for the off-heap memory. So that would be spark.memory.offheap.size. and the default size is set to 0. So you have to define a size for this. Consider you define 512 MB. Okay. In this case, what will happen is Spark will go ahead and procure a 512 MB memory in the worker node. Okay. So consider this is your 512 MB memory, and this would be your off-heap space. Okay. Now, off-heap space are majorly used to store your cache data. Okay. So consider this is your storage memory. Now you are not able to fit your data into the storage memory. You can go ahead and spill this data to off-heap now. Okay, rather than spilling it to disk, you can go ahead and spill this to Off-Heap. Now, this is a better option than disk. It comes with own limitations. The biggest limitation to this is GC is not maintained by JVM here. GC is garbage collection. It means whatever memory or object you release after your use, you have to manage the garbage collection yourself. JVM only manages garbage collection on-heap memory. Okay, now this memory is not maintained by JVM, and this is why you have to write your garbage collection code here. Okay, so this is one of the limitations. If this is not done properly, you will run into issues. Okay, now this is the main reason where OFF is being used. Now, since we are discussing garbage collection, let's understand what is this GC. Okay, now if you remember our storage and execution unified memory, so this is our storage and this is our execution memory. Consider you have stored some of the data in the execution side. Okay, now execution needs to expand and it needs to use its own space. So in that case, you will go ahead and evict this out of the memory. Okay, so it is the duty of the garbage collection to remove objects which are no longer necessary. So the garbage collection usually frees up space in the memory. Okay, so it removes all other unnecessary objects which are lying in your memory and it frees up the space. Okay, now there might be a case where your garbage collection cycle is taking too long in order to free up space, and you will see your Spark program halted in that case because it might be waiting for that memory to free up and your garbage collection cycle is taking too long. So you might see some log messages printing like garbage cycle is running. Okay, in those cases as well, the memory does not get freed, you will run into out of memory errors. Your Spark program might also fail because of longer garbage cycle runs. Great. I hope you understand a lot of things about Spark memory today. You understand what is on-heap memory, what is off-heap memory, what are garbage collection cycles, how the on-heap memory is distributed for Spark. Let's go ahead and see one of the example of out of memory errors. Now, I am in my Jupyter Lab environment. We are going to create one cluster today. We are going to request for 8 cores total and one executor with 4 cores. And the memory for executor would be 512 MB. So in total, we are going to get 2 executors, each with 4 cores and 512 MB. So let me just show you the cluster I'm running. So I'll quickly go to Spark Master and you'll see 2 worker nodes running. Okay, and each one has around 6.6 GB of memory and 8 cores each. And we are going to request 2 executors, one in each with just 512 MB memory and 4 cores. Now, if you want to follow along in this course, what you need to do in order to set up your cluster is you need to go to a URL which is github.com/Shubham Kharwal. Okay, now you need to switch to this particular repository, which is Docker images. And under this repository, once you clone this, or you can just go ahead and download the zip from here. Once you do this, you need to go to this folder, which is PySpark cluster with Jupyters. And in the README, you can find the commands that you need to run. And once you do this, in your Docker desktop, you will see a container like this, where this is the Jupyter Lab that you are going to use. And this is the cluster where you have one master and 2 worker nodes. Okay. Now I'm back in my Jupyter Lab notebook. We have already decided that we are going to create 2 executors, each with 4 cores and 512 MB memory. Okay. Let me just go ahead and generate our Spark session. Great. Now if you see, my Spark session is ready. Let me just go ahead and refresh the Spark UI, which would be in the port 4040. So let me just refresh this. And you can see my Spark UI is up and running. Okay. Let me just go back. Now we will implement the memory calculations that we have seen in theory. Okay. So the memory that we have specified for the JVM process or the executor is 512 MB. And this is for each executor. Okay. So our on-heap usable memory is around 89% of 512. Right. Let me just go ahead and type 512 into 0.89, okay, which is 89%. So if I run this, you can see this is approximately 455.68 MB. So let me just copy this. And now we know that we have to remove the reserve memory, which is 300 MB out of this total memory, which is usable. Okay, so let me just put it here and let me just subtract 300 out of it. If I run this, you get 155.68 MB. Okay, so this is the memory which is left out after reserved memory. Okay, so now we will split this memory into two. One would be the Spark memory and other would be the user memory. And we know that we use Spark memory fraction, the value is 0.6 for that. Okay, so 60% would be the total Spark memory and 40% would be the user memory. Let's go ahead and see what is the unified Spark memory. So I'll just say 155.68 into 0.6. Okay, so this is the unified Spark memory. Okay, so this unified Spark memory means this is storage memory plus execution memory. Okay, so you see this value as 93.4. Let me just go back to my Spark UI first. So I'll go back to Spark UI and let me go to the Executors tab. So now if I scroll down, you can see we got two executors, 0 and 1. Okay, now if we see the storage memory, this is 0 bytes right now, but the total memory that you see is 93.3, means this is the unified memory that is available on each of the executor. Now if you see that 93.3 MB is available on the 0th executor, and on the first executor you also see 93.3 MB, which is approximately same that we calculated. Okay, 93.4. Now the calculations can be some MBs here and there, but you will always get the approximate amount here. Okay, so 93.4 is the approximate MB, and you can go ahead and see that the unified memory is 93.3 MB. Okay, out of this, if you store something in storage, you will start seeing that memory here. Okay, let me just go back. So this is our unified storage memory. Now what would be the user memory? That would be 155.68 in remaining 0.4, which is the 40%. So let me just run this. So this is the 62.27, which would be available for user memory, and we are not going to talk about this. Okay, so now that we understand this is our unified memory, which is 93.4. Let's see if the storage fraction is 0.5. So how much storage memory is there? Now again, this is not a hard limit because this is unified memory, and storage and execution memory can expand as per their requirement. Okay, but let's, if the storage fraction is 0.5, which is 50%, so what would be the value? So let me just paste it here, and I'll do 0.5, which is 50%, which is 46.704. Okay, so the execution memory will still be same. Okay, so this calculation is same for execution memory, which is 46.7. Okay, now we have 4 cores in each of the executor, right? So if we see what is the amount of memory available per core, so that would be divided by 4. Okay, 11.6 MB per core. Okay, but this is not the hard limit. Okay, great. Now that we understand how the memory is divided, let's go ahead and see a scenario where an out of memory error can happen on your executor. Okay, so before I can do that, I'll just disable AQE. Now AQE has no impact on this, but in order to understand this easier, I'll just disable AQE. Okay, so I've just disabled AQE. You can go ahead and set this configurations in order to disable AQE. Now I have some files already present under this location. Now data is the location which is mounted throughout the executors and the worker nodes. Now I have kept the file in the same location. Now if you want to follow along, make sure you also keep the files at this location. Okay, so let me just run this. And now if you see, I have 4 files here. Now we are going to work with only 3 files, but let me tell you what are the content of this file. Okay, each of the file contains some of the paragraphs, and we are going to count number of words today. So it is a pretty simple problem. We will read data from the files and we are going to count the number of words. And each of the file contains some of the lines and some of the paragraphs of data. Okay, now if you notice, the XS, which is the smallest file, is of size of 11 MB. Now I have one more which is greater than that. It consists of 21 MB. Okay, now there's one more file where the whole data is in a single line. Okay, which is around of 11 MB, which is the same size of that of XS. Okay, so let me just show you the data. So I'll quickly copy this location from here and I'll open a cell. Okay, so I'll just go and change this to bin bash. Okay, and I'll change the location to this, and I'll just type ls minus ltr so that you can see the files. Let me just show you first the content of single line file. So if I copy this and if I do head and if I paste it here and if I run, you can see this whole data is in a single line, and that is why this whole line is getting printed, because this is all in a single line. So let me just put Control C. Again, I'll do ls minus ltr. Okay. Now for the same file, we have data in multi-line format. You can see it in this file. So I'll just copy this and I'll do head and I'll paste it here. You can see here the data is in multi-line format. Okay. Now S is just a bigger version of this XS file. Okay. And please ignore this cities file as of now. Now, the first thing that we are going to do is let's cache one of the file, which is single line file here, right? Let's go ahead and cache this in our memory. Let's see how much memory it consumes in our storage. Okay, so to do that, I'll just read df equals to spark dot read dot, I'll use the format as text. Okay, and I'll not specify any option. I'll just write load. Okay, and I'm going to load this data. So I'll just copy this location first, and then I'll copy the name of the file that we are going to load. Okay, and let me just run this. Okay, our data frame is ready. Let's go ahead and cache this. Now cache is by default memory and disk deserialized, right? So let me just cache this. So I'll just type cache dot, and now we need to put an action in order to cache the data that we know from our previous video when we learned about caching, right? That in order to cache, you need to provide some action. Let's do an action which is called count. Okay, let me just run this. Great. Our data is cached and we know that the whole file is in a single line, and that is why the output that you see is 1. Okay. Now let me quickly go back to Spark UI, and if I scroll up and if I go to storage, if I open this, you can see here that the size in memory is approximately 30 MB. Now it has been read by 3 partitions, but one of the partition is skewed, which is reading the whole data. Rest all are reading some data, right? Which is very less, but one of the partition is reading the complete file. Okay. So if I go back, in total, it is storing the file in the memory completely, which is 30.8 MB. Okay. So if I go to executor now, if I scroll down, you can see here that the whole 30.8 MB is the storage memory stored in executor 1. Okay. Now you can see that it is consuming the particular memory here. Okay. So out of 93.3 MB, it has already consumed 30 MB for storing the file. And the other executor is storing some KBs of file, but that's okay. Our data is getting stored majorly in executor 1 and it has already consumed 30.8 MB. Okay, so this is where if you do caching, the data gets stored into the storage memory. Okay, so let's go back to our notebook. And now that we know our data is stored, let's go ahead and count the words. Now, we have already done this previously in our videos. So today I'm not going to explain much about it, but I'm going to show you how we can count the words. Okay, so what I'll do is I'll first write df final. Okay, and I'm going to use brackets for this. Now the first thing that we are going to do is we are going to convert the whole string into lower string so that we can count the words easily. Okay, so before that, let me show you the column that is present. So I'll just type df dot print schema. So if you see, there is only one column called value. Okay, so let's go ahead and overwrite the same column. So I'll just type df dot with column, and the column name is value. We'll overwrite the same column, and we are just going to convert lower. Okay, so that all the string get converted into lowercase. Okay, now this is done. We have converted the whole string into lower, and we are again saving it back into the same column, which is value. Okay, now the next thing that we need to do is we need to split the whole string into words. Okay, and we can do it using spaces because words are separated from each other using spaces. So let's go ahead and split them up. So for that, I'll go ahead and create one new column. So I'll just write with column, and I'll just type splitted val. Okay, and we will use a function called split, and we are going to split the column which is value, and we are going to split it based on spaces. Okay, so what it will happen is it will give us an array where you will have words splitted like this is and okay, you will get an array as output of this column where the words will be splitted. Okay, now we'll have all the words in an array. Okay, now we will explode this particular array so that we can bring this in column format. Okay, to do that we will use another function which is known as explode, and we have already discussed all of this in length in this video. Let's go ahead and use with column for this, and I'm gonna name this as exploded val. Okay, and we are going to use function called as explode, and we are going to explode this splitted val here. So I'll just use this. Okay, now this is going to explode this array into a single column. So is and everything would be under the same column, which is exploded val. Okay, Now let's just drop this splitted val because we no longer need this. So I'll just type drop and I'll remove this column because work of this column is done. Okay, and we will also remove the value column because that is also no longer required. Okay, now that we have a column known as exploded val where we have all the words in a single column, let's go ahead and do a group by in order to count. Okay, so I'll just type group by based on the word which is splitted val. Okay, and we will do aggregation. What we will do, we will just do a count of 1. To do that, we'll just type count, and again we cannot directly use 1, so we'll use literal for that. I'll just type lit of 1 and we'll do count, and we'll just alias this as cnt. Okay, this is for count. Okay, so let me just close this group by and we are done. Okay, so we have just first expanded the particular line in an array using split command, where we will use space in order to separate out words, and then we will convert this array into a single column using explode, and then we are dropping all unnecessary columns, and then we are doing a group by in order to count the number of words. Okay, so this is done. Let me just import all the functions that we used. Okay, my bad. I just used the long column. We need to use exploded val here for group by. Okay, so let me just run this again. This completed successfully. Now let's go ahead and use no off format in order to run this. You can go ahead and also use show command in order to see this. Let's do it using show command. So what I'll do is I'll just type df final dot show. Okay, now one thing to notice here, since we are exploding here, so each column that is of size of around 30 MB will get multiplied by the number of words. Okay, because we are exploding here the data. Okay, so let me just run this and you will see that the executor will start crashing because the data is getting multiplied here in the memory. Okay, because it has to bring in the whole single line into the memory and then explode it. So explosion would cause multiplication of record. So let me just run this now, and now this is running. Let's just wait for a minute. Okay, now if you notice, after refresh, we can see failed tasks. Okay, so the tasks started failing. Okay, in executors, you can see this executor is dead now. It will go ahead and add one more executor to process this. Okay, you can see one more is active now. Let's go ahead and see the jobs. So I'll quickly go back and I'll click on jobs. I'll click on this. If I scroll down here, if I click on the stage, if I go down, now if you see here, out of memory errors. Okay, this is happening because we are reading a record which is quite big and in a single line that cannot be splitted, and we are multiplying it using explode function. Okay, so the explosion is causing that record to be multiplied inside the memory, which is leading to out of memory error. Okay, so if I wait for a few more minutes here, you will see it would fail of out of memory error. So let's just wait for it and let it fail. Now this job has failed. If I scroll down, you can see it has failed because of out of memory error. So now we understand why this job has failed. So what can be the better way? Let's go ahead and rather than reading it in a single line, let's go ahead and read this in multi-line format. And see this XS file that we discussed previously. This is containing the same data but in multi-line format. So let me just go ahead and run this and let me show you the data. So I'll just type df dot show. So now if you see, this whole data is being read in multi-line. So each line which is stored in a different record in this particular table is not of that big size. Okay, so let me just go ahead and use this file to count the words. Okay, so I'll just scroll down, and in place of cache, I'll not do cache here. Let's go ahead and run the print schema. You can see same value. Okay, so let me just run the same command to count the words. Okay, and let me run this show command now. Great. Now you can see the output. You can see exploded val and count of the words present. Okay. Now you understand the reason for it. Okay. Because the lines are not so big and those can fit in the memory. In our previous case, a single row was being read into the whole memory, and once exploded, that row caused out of memory. But this time, since each of the rows that are being read are very small, so they can easily be exploded in memory, and thus you can see the count here. So now you can understand how a simple change in data can avoid out of memory errors. We have not expanded at all our memory. We are still using 512 MB memory, but the only change that we did is rather than reading the whole data in a single line causing out of memory error, we are now reading a multi-line file where each record is storing one line and the size of the line is smaller. Okay, now if you think this is just because this is a smaller file, you can even read bigger file. So let me just read it for S. So I'll just change this. Again, this is multi-line file. So if I run this again, you can see the lines are being read as one record each. So if I scroll down and if I run this command again, and if I go ahead and do a no op this time, no op is used for benchmarking. It simulates as if you are writing data somewhere, but it will not actually write the data. So let's go ahead and use this tf final from here, and let's write this in no-op. So I'll just use write dot format, and I'll use no-op for this. Okay, and I'll write mode as overwrite, and we will put save. Okay, this is basically used for benchmarking. So let me just run this. Now if you see, it has just finished in few seconds. Okay, let me just go back to Spark UI. Let me go to SQL data frame. So if you see, this is the job we're talking about. Let me just click on this. If I go to the job, which is 9, so if you see here, we are scanning, then we are doing an exchange here, okay, because of counting. So it has used a total of 6 partition to read the data, which is 20 MB, and then it is writing a shuffle of 20, okay, and then it is using 200 tasks in order to read the data. So now you understand, even if I increase the size of the file, my job or my operation is complete without any out of memory errors. So you understand how this thing works. Again, there is one more thing. Consider you have a multi-line splitted file like this. Okay, let me just use access here. And now what you try to do is, rather than reading it in partition format, what you try to do is you try to read the whole file into single partition using options like option whole text, and you specify this as true. Okay, if you specify this option, it is going to read the whole file in a single record. Okay, so let me just show you this. So if I run this, if I run show, you see it has read the whole multi-line file in a single record. Again, now if I run this, it will again fail out of memory errors, because single line, it will again try to explode, it will run out of memory. Okay, so you have to be very careful of the options that we are going to use. Okay, so sometimes bad code leads to out of memory errors, so it is not always that you have to expand your memory in order to work it out. Okay, now if you think this is all because I have disabled AQE, you can go ahead and enable AQE and try this out. It will still fail because the logic will still remain same in the background. Okay, so it is very important that you understand how memory works and how your bad code can lead to out of memory errors. Okay, sometimes you need to expand your memory in order to make things work. Sometimes it is all because of bad code. Okay, for example, this is a bad code. If we remove this, we can read this in multiple partitions, and the records will get splitted into multiple rows. Okay, I hope you understood a lot of things about Spark memory and out of memory errors today. This video was lengthy, but it gives you a lot of vital information that you need to know. With this, I'll conclude this video here. I'll see you in next video. Till then, keep learning, keep growing, and keep sharing.